Welcome to Brain Vision.
Okay, our question states that another experiment you can do also uses the radius of the Earth. The sun sets, fully disappearing over the horizon as you lie on the beach. Your eyes are 20 centimeters above the sand. You immediately jump up. Your eyes are now 150 centimeters above the sand, and you can again see the top of the sun. If you count the number of seconds denoted as t until the sun fully disappears again, you can estimate the radius of the Earth. But for this problem, use the known radius of the Earth and calculate the time t. Okay, so I have drawn here drawn the Earth as a green sphere, and I've denoted the radius of the Earth as the red line labeled as r, and the radius or the distance from r to the new height of the eyes after standing up, which I have denoted as h, as r plus h. You can then draw a line between the eyes of the individual who is standing to the point in which the sun appears to be setting as point B. And then I also denoted point A here as the point at which the sun appears to be setting the first time. The dotted line denoted as 1 is the direction of the first sunset, and the dotted line denoted as 2 is the direction of the second sunset. The angle between these two dotted lines is theta, and from geometry, that's going to be the same angle as between r and r plus h. And conveniently, r plus h, and d make a right triangle here, which I showed by drawing that little square in the corner where the right angle appears. So this is actually really useful. We can use this fact to make use of Pythagorean theorem, which states that the square of the hypotenuse of a right triangle is equal to the sum of the square of the two sides. So the hypotenuse of our triangle is r plus h. So r plus h squared is going to be equal to the sum of the two sides. So d squared plus r squared. Okay, but we can go ahead and carry out the square of r plus h. If we do that, we have r squared plus h squared is equal to, plus 2rh. That's from carrying out the sum, that's from carrying out the square of r plus h squared. Well, another convenient fact here is the fact that h is very, very small compared to compared to r. So r squared is going to be significantly larger than h squared, as well as 2 times r times h is also going to be significantly larger than h squared. So h squared here, let's just write that fact out so we have it visualized, is much smaller than r squared plus 2rh. So those values are going to dominate that side of the equation. So we can actually go ahead and just ignore h squared. So this gives us, we're going to rewrite Pythagorean theorem now as d squared plus r squared, sum of the two sides. But our hypotenuse now is going to be rewritten, since we're ignoring h, go ahead and cross that out, as r squared plus 2rh. All right. Well, by doing this, we see that r squared is also going to cancel out on both sides of the equation. So we can go ahead and cross that off. And now we are able to solve for d, which we did not know before. D is equal to the square root of 2 times r times h. Okay, the other thing we don't know here is theta. So we're going to make use of the trigonometric identity of tangent theta here is equal to the opposite of theta divided by the adjacent to theta, the adjacent being r. So it's going to be the opposite, which is d over r. Well, we just solved for d. We know that d is equal to the square root of 2rh, and we know what r is, so let's go ahead and solve for theta. We have all the pieces in place to solve for theta. So theta is going to be the inverse tangent, which is denoted as tangent to the minus 1, of d, which is the square root of 2rh. So we'll just go ahead and write it as that. All over r. If you plug in the values for r and h, and you carry this out, you plug it into your calculator, you find that the theta value is 3.66. There's a decimal place here, times 10 to the minus 2. And the units here are degrees. So if your calculator is in radians, you're not going to get that value. So make sure your calculator is solving for things in units of degrees. Okay, so we ran out of room on this page. So let's go ahead and open up another page here. Okay, and we're going to make use of the fact that it takes for one full rotation. So one rotation, we'll just abbreviate it as ROT, for the Earth is equal to 24 hours, right? But it's also equal to 360 degrees for one full rotation, right? As far as degrees goes. Okay, so we have there our conversion between the degrees and time it takes here on Earth for one full rotation or 360 degrees to take place. So we're going to go ahead and make use of that relationship there because we know theta, we know the angle of rotation that we have relative to the full rotation, which is 360 degrees. So we know that ratio, right? And the ratio we want to find is the ratio of the time it takes for theta to occur, for that amount of rotation to occur, relative to the full amount of time, which is 24 hours. Okay, but this is going to be relatively small, maybe on the order of a few seconds relative to that 24 hours. So let's go ahead and convert hours into seconds to work with more relevant, nicer units. So 24 hours, HR, not just R, multiplied by the amount of seconds in 1 hour, which is 3,600 seconds per hour, will give us time in 24 hours, which comes out to be 86,400 seconds. Okay, so now we have everything we need to solve for time t. So if we solve for t, we see that t is equal to theta over 360 degrees multiplied by our 86,400 seconds. Okay, and that comes out to be 8.8 seconds. So that's how much time passes between the first and the second sunset. All right, and that, go ahead and box that in because that is our solution.